Alright, so let's say we have two vector spaces. Let's say our vector spaces are just R2. And we have some kind of transformation. This transformation goes from, let's take a look. Transformation goes from 1, 1 to 2, 0. And another one is 1, 0 to negative 1, 0. And then the question asks, how do we represent this transformation with respect to the standard base? Okay, so the first thing I want to talk about is matrix representation. How do we represent a transformation? Let's call this transformation H. H stands for homomorphism. It's a transformation, linear transformation. It's a transforming, mapping one vector space onto another that maintains the structure of linear combinations. So, how do we actually represent this linear map in terms of basis? So let's say we have a vector space V and a vector space W. Okay, each one of these can have their own basis. Let's call the basis V. Let's call this B. Let's say the the basis of W is D. What we define as the representation of the map. We're going to represent the map by taking each vector inside the first basis. We're going to project it onto the other one. So, beta 1, we're going to project that into this projection. And then we're going to represent each of these in terms of a basis of the second vector space. We're going to write a representation of each of these projections. Okay, so I'm just going to write this again just to keep track. And then we're going to define the representation of the map itself to be the combination, kind of just adjoining all of these representations. So we're going to put this one here, and then put this one here, and then any more over here. And so basically this will be our kind of matrix. If this was 0, 1, this was 2, 1, this would basically look like 0, 1, 2, 1 here. And that's our representation of the map itself. The next thing we need to know is how to apply a map to some vector, right? Let's say we have a vector. Let's say we have a vector V within vector space V. And then how do we actually apply this to get the image in vector space W? So the application of a vector, and this is just this is a definition. The representation of this application in terms of with respect to the basis of the vector space into which you are projecting is equal to the representation of the map itself times, this is the matrix vector product, the representation of the vector with the basis in the vector space V. So this matrix vector product right here, I'll explain later, but this is the other definition that we'll use here. Okay, so let's go back to our problem. We know that we're given a couple of vectors, and we're given this projection, and it's asking us what is the representation of H with respect to the standard or natural bases. And other way to say this is, if we take 1, 0, and we project that, and we take 0, 1, so this is the standard basis, then what does this become? If we can find these, then we can use, the definition of a matrix representation. That'll give us the matrix representation with respect to the standard basis. So what we can do first, we know what 1, 0 projects to already. That's already -1, 0. Now the question is, what does 0, 1 project to? So that's the question. Now 0, 1, now that's where we use this second one. So first we want to represent this 0, 1 in terms of the basis that we have. So let's say our basis that we already have one basis. We know how to represent this vector in terms of the basis b. If we define the basis b to be 1, 1 and 1, 0, and we can see that this b is a valid basis because it spans the vector space of real numbers. You can produce any two real numbers, two components of real numbers based on these two. So we can write the representation of I'll write this as 0, 1 here. Right? We can write this as 0, 1 represented for this. This can be 1, -1. If you take one of these and then subtract one of these, we'll get 0, 1 here. Okay, so that gives us this part. So the second part that we want is the representation of this map in terms of our basis. So this map here will take B to be the same basis, right? And then we're taking D here will be the natural basis of vector W. So we'll do that. And then we'll use this same system to find this. So what we'll do, we're going to take each vector in this basis. We're going to project it. Now we know the projection. So 1, 1. We know the projection is 1, 1 to 2, 0. And so we're going to represent this in terms of this natural basis. So if I look at 2, 0, represented natural basis is just 2, 0. And so in the end here, we can write this, we can represent H with respect to this basis here, as well as the natural basis here. We can write this as just the adjoining of all of these. So this is 2, 2, 0, and -1, 0. Okay, so we have this, and we also have the representation of 0, 1 equals 1. So all we need to do now is find the matrix vector product of these two. So that'll give us 2 2 times 1 is 2, plus 1 is 3. And then 0 times 1 is 0, 0 times -1 is 0, 0 plus 0 is 0. So that gives us the representation here, the representation of, remember for D, we use the natural basis of the projection of our vector. All these should have B's in front of them. There should be B, epsilon 2. All these should have to denote that this is a representation. So H, so we know that our representation of 0, 1 is equal to the representation of, is equal to 3, 0. Here. Now 3, 0, of course, with the basis, with the standard basis, is also just equal to 3, 0. So now that gives us the projection is equal to 3, 0. And now we know the image of 0, 1, we know the image of 1, 0. We can just write the matrix representation. That'll just be, remember, this is the basis. These are the vectors in the basis. We project each one and then represent that in terms of the natural base of the basis of the second vector space, and that will give us a representation of the map with respect to our two bases, except in this case B is the natural basis because it's 1, 0, 0, 1. And it's also natural basis for the second one will be equal to, now look, B1 projected -1, 0, represent that in terms of natural basis, that gives us -1, 0. And then the other one, so describe this, 3, 0, and that gives us the representation of the linear map in terms of the standard bases.